Glass is one of humanity's most fascinating materials. It's strong yet fragile, solid yet seemingly fluid, transparent yet powerful. But here's the twist. Glass is not a typical solid. From a scientific point of view, glass is an amorphous solid, meaning its atoms are not arranged in a regular repeating crystal pattern like in metal or salt. Instead, they're frozen in a disordered, liquid-like structure, a snapshot of molten material that never fully crystallized. The main ingredient of glass is silica, better known as quartz or sand. It makes up around 70 to 75% of most glass compositions. To it, manufacturers add sodium carbonate, lowers the melting point of silica, limestone, strengthens the final structure, and various metal oxides, which define the color and properties of the finished glass. For example, iron oxide gives glass a green tint, cobalt oxide turns it blue, selenium or copper oxides produce red or golden hues. Each batch is mixed with precision. Even the tiniest imbalance can affect transparency, strength, or color. From sand to the furnace, not all sand can be used to make glass. The sand must be extremely pure, with very low levels of iron and organic matter. Only this kind of quartz sand can withstand the high temperatures needed for melting. Once all ingredients are perfectly measured and blended, the mixture is loaded into massive industrial furnaces where temperatures reach 1400 to 1600 degree Celsius. At this stage, something remarkable happens. The rigid crystal lattice of quartz breaks down and the atoms start moving freely, forming a thick molten liquid, molten glass. From ordinary sand, fire creates one of the most important materials in human history. Once the raw materials melt inside the furnace, the true art and science of glassmaking begins. Inside those fiery chambers, at temperatures exceeding 1500 degrees Celsius, the crystalline structure of silica completely dissolves. Atoms of silicon and oxygen lose their rigid order and form a viscous, glowing liquid, molten glass. At this stage, the glass is alive, thick like honey, glowing like lava, and ready to be shaped by human skill and technology. Refining. The pursuit of perfect clarity, even the smallest imperfection can ruin a batch of glass. As the ingredients melt, gas bubbles and impurities form in the molten mass, remnants of carbon dioxide, moisture, and chemical reactions. To remove them, the glass must go through a refining or homogenization process. This happens through two main methods. Physical refining. The molten glass is allowed to rest for several hours, letting bubbles naturally rise to the surface and escape. Chemical refining. Certain compounds, such as arsenic oxide or nitrates, are added to break down gases and stabilize the melt. The result is a perfectly pure, uniform material, ready to become anything from a bottle to a skyscraper window. Forming how shapes are born, at around 1200 degrees Celsius, molten glass is fluid enough to shape, yet thick enough to hold structure. This is when glassmakers use different techniques to create its final form. Float glass method. The molten glass is poured onto a bath of molten tin. Because tin is denser, the glass floats on top, forming a perfectly flat surface. This technique produces window panes, mirrors, and smartphone screens. Blowing and pressing, a blob of molten glass is inflated or pressed inside a mold using air or mechanical pressure. This ancient technique, over 2,000 years old, still makes bottles, lamps, and ornaments. Fiber drawing. When glass is pulled into ultra-thin strands, it forms fiberglass and optical fibers, used in everything from insulation to internet cables. Each method requires precise control of temperature and viscosity. Even a few degrees off can cause the glass to lose transparency or deform during cooling. The physics of molten glass is neither a true solid nor a conventional liquid. It's a supercooled fluid, where the atoms constantly shift yet remain bonded. This hybrid state gives glass its incredible malleability while hot and rigid strength once cooled. Inside the furnace, this glowing river of silica is the bridge between chemistry and art material that carries within it both chaos and order. From here, the molten glass flows onward, toward cooling, strengthening, and the transformation into a material that will outlast centuries. When glass takes its final shape, the work is far from over. In fact, the most critical part is only beginning, the cooling process. This is the stage where glass decides whether it will stay flawless and strong or crack under its own inner stress. Cooling, the art of patience. Freshly shaped glass can reach temperatures near 700 degrees Celsius. If it cools too fast, the outside hardens before the inside does, creating internal tensions so intense that the glass can shatter instantly. To prevent this, glass goes through a process called annealing. It's slowly cooled in long, temperature-controlled ovens known as layers. Here, the temperature is gradually lowered over many hours, allowing internal stresses to release evenly throughout the structure. Without annealing, no glass product, from window to wine glass, would survive for long. Tempering, making glass 5 times stronger. Some types of glass, such as car windows, phone screens, and safety panels, require more than just stability. They need true resilience. That's where tempering comes in. In this process, the glass is reheated to around 650 degrees Celsius, then cooled extremely fast using blasts of cold air. The outer layers contract first, while the inner layers cool more slowly, locking tension inside the structure. This controlled imbalance gives tempered glass its unique strength. It's up to 5 times stronger than ordinary glass. And when it finally breaks, it doesn't form sharp shards, but small, blunt fragments that don't cut the skin. That's why your car windshield and phone screen don't explode into razors when they crack. Coloring and optical properties. Glass isn't always transparent. Its color and behavior with light depend on chemical additives and atomic interactions. Iron oxide gives green hues, cobalt oxide produces deep blue tones, copper or selenium create reds and ambers, titanium or cerium oxides improve UV resistance, boron increases heat resistance, like in laboratory glass. Each metal interacts with light in its own way, absorbing certain wavelengths and reflecting others. That's why colored glass looks vibrant and pure. Its color comes from physics itself. The science of light and color. Light waves passing through glass interact with its atomic structure. If certain wavelengths are absorbed, only specific colors reach your eyes. This is why stained glass windows glow so vividly. They're living demonstrations of quantum physics and art combined. Through precise control of additives, engineers can craft glass that filters UV rays, amplifies light in telescopes, or even redirects laser beams. From cooling ovens to colored masterpieces, this stage transforms molten chaos into lasting beauty, turning fragile material into the foundation of modern civilization. Glass has been part of human civilization for thousands of years, but its greatest chapter may still lie ahead. From ancient sand and fire, it's evolving into an intelligent material, a substance that can generate energy, repair itself, and even survive in space. Smart glass material. That thinks. The most futuristic form of glass is smart glass, designed to automatically adjust how much light or heat it allows through. Using electrochromic or thermochromic layers, it changes transparency when voltage or temperature shifts. On a hot summer day, the glass darkens to block sunlight and reduce cooling costs. On a cold winter morning, it stays clear, letting warmth inside. It's already used in skyscrapers, modern homes, and electric cars, helping save energy while improving comfort. In the near future, smart glass could become the default building material, turning entire cities into living, responsive ecosystems. Glass that generates energy. Scientists have also developed transparent photovoltaic glass, a material that looks like a window but works like a solar panel. Inside, microscopic layers of semiconductors capture sunlight and convert it into electricity without blocking the view. This innovation could transform architecture. Skyscraper facades could soon power themselves, and cars could recharge simply by parking in the sun. Glass is no longer just a barrier, it's becoming a source of energy. Self-healing glass, inspired by nature. Imagine a phone screen that repairs its own scratches, or a window that seals its cracks overnight. That's the goal of self-healing glass, created using metallic ions and polymer networks that reconnect chemical bonds when exposed to air or heat. It's the same idea nature uses to heal skin or bone, except now we've taught matter itself to recover. Early versions of self-healing glass are already in laboratories, And soon they could become standard in smartphones, vehicles, and even space stations, places where replacing materials isn't an option. Glass in space strength. Beyond Earth, beyond our planet, glass is critical for exploration. Telescopes, satellites, and Mars rovers all rely on ultra-pure fused silica glass that can withstand radiation, cosmic dust, and temperature swings of hundreds of degrees. NASA and ESA engineers use specialized quartz-based glass composites to protect instruments, optics, and even human habitats. Some experimental forms, like metallic glass, combine the transparency of silica with the strength of steel. In the vacuum of space, glass is not fragile. It's a survivor. Tomorrow's transparent revolution in research labs, new generations of glass are already being tested. Nanostructured glass that never gets dirty, antibacterial glass for hospitals, flexible glass that bends like plastic, and optical glass that adjusts focus automatically. The glass of the future won't just let us look through it, it will react, protect, and communicate. From molten sand to smart cities and space exploration, glass has always reflected who we are: curious, inventive, and never satisfied with limits. Every window, every lens, every screen is a silent reminder that humanity learned to turn fire into light and light into knowledge.